Hello everyone. Now we are going to take a look at what are different multi-GPU variations that are supported in MGPU sim. These include different models of multi-GPU as well as the associated memory models such as either unified or non-unified memory. So the first thing is the discrete versus unified GPU, which are two models that we support for multi-GPU simulation in MGPU sim. In a discrete GPU model, all the GPUs are exposed to programmers. So the developer or the program writer is responsible for splitting the kernel across multiple GPUs. On the other hand, in the unified GPU model, all the GPUs in the system, be it 4, 8, or whatever any number, is virtualized and presented as a single GPU to the user. So the user doesn't really have any control over splitting the kernel. So who splits the kernel or who does the distribution of work in unified GPU is the GPU driver, which handles this distribution of work groups across GPUs. With the discrete GPU model, it allows for more control over how the kernel is scheduled, and you can partition accordingly. So benchmark kernels or that are supported in MGPU sim, or even if you in the future, if you want to write a new benchmark to support this, would need to be modified slightly to support this. So currently we have 10 workloads that support this discrete GPU model. On the other hand, in the unified GPU, we do not really need any modification to the kernel, and there are 15 workloads that are part of the current suite that support this model. Now, coming to unified and non-unified memory. So as we know, unified memory is a very popular feature that eases the development of multi-GPU programs. As such, we support a similar mechanism in MGPU sim as well. This is done through the allocate unified memory API, which behavior is similar to CUDA malloc manage. That is, the driver and the runtime is responsible for handling the movement of data. With non-unified memory, all the benchmarks use the allocate memory API. So the data is actually allocated on a GPU. And the distribute API, which is again one API that is provided by a driver, is used to distribute this memory to multiple GPUs. So all the mem copies actually happen before this program is executed. Now, in terms of unified memory, we model a first touch based page migration policy. So the data is allocated on the CPU, and then at runtime, based on demand, this data is migrated from the CPU to the GPU. On the other hand, for non-unified memory, all the inter-GPU memory accesses use RDMA. So in the case of the unified memory, all future accesses to the same page, once the page has been migrated the first time, also uses RDMA. In the non-unified memory, there is no form of page migration since the data is all copied based on the distribute function to the different GPUs. So there's no runtime page migration that is happening. So all these lead to basically 4 different combinations that are currently supported in MGPU sim. The first is the discrete multi-GPU non-unified memory. So here, both the work distribution and the data placement are controlled by the programmer. The second model is discrete multi-GPU unified memory. In this scenario, the work distribution is controlled by programmers as to how the kernels are split. However, the data is allocated on the CPU and migrated to GPUs at runtime. The third model is the unified multi-GPU non-unified memory. In such a scenario, the work distribution is actually controlled by the driver, whereas the data distribution is also controlled by the driver. So there's no programmer control here. Since the programmer only sees one GPU, so both these things have to be orchestrated by the driver. So the driver would internally distribute this data before the kernel launch happens. So the mem copies still happen before the kernel launch. However, the user does not really do this distribute action, and the driver does it on the user's behalf. And the fourth model is the unified multi-GPU and unified memory. So here, the work distribution is also controlled by the driver. At the same time, the data is not allocated across GPUs, but is allocated on one CPU and then migrated to GPUs at runtime. So all of these provide different models that a user can configure to do his own research based on the platform that he's most interested in. So in the next time, we're going to take a look at a hands-on demo as to the different forms of multi-GPU that we currently support.